Okay, hello folks, how you going? Alright, so I'm in a new hotel room now. It's wedding season now, so there's a bit of chopping and changing, but I think I'll probably be here for the rest of my stay, which is a couple of weeks. And I've got my board behind me, as I did in the last place. And as you can see from the title up there, I'd like to talk about the sun. Now, obviously there's a lot to be said about the sun, but I'm just going to put a couple of things on the table, just to give the fence sitters something to think about before they fall into the abyss of this flat earth cult. Okay, and of course if you're a flat earther, then you need to look carefully at this. I would suggest that you do look carefully at this, and then perhaps if you have any intellectual honesty, then perhaps just rethink some of the things that you believe and that you heard from your charlatan gurus like Jeranism and Globebusters and people like that. And just while I'm talking about them, if you think they actually believe that the earth is flat, then you're even more delusional than we expect. Okay, these people don't think the earth is flat. For them, this is just a means of making money. And typically, it's pretty easy money for them. Okay, enough of that. Let's have a look at the sun. So first of all, we'll look at it in terms of what the claims are. All right, and one of the major claims about the sun is it's close. So it's small and it's close. Okay, let's have a look at what we do know about the sun and why we know what we do. Okay, so look at the board. Okay, first of all, the distance to the sun. Well, there's a number of ways that has been determined. Cassini, using parallax and Mars, and basic trigonometry. So Cassini is able to observe Mars, and from that use some basic trigonometry and get within about 6% of the distance to the sun. So even then had a pretty good idea that the sun was a long way away. Okay, so think about what 6% of 93 is, and that'll give you a pretty good idea of roughly what Cassini thought about the distance to the sun. It certainly wasn't within a few miles. I've heard flat earth proponents say that they think it's probably just 7 miles, as Marilyn from that proselytizing show says, which would mean that it would be pretty much competing with the same space as some aircraft, and then goes up to, I don't know, 20 or 30,000 miles or something like that, or 3,000 miles, sorry. Yeah, I think 3,000 miles I've heard. Anyway, regardless of that, apparently inside a dome, which is another thing. Now, while I mention that, to be fair to other flat earthers, for instance, like Dell, the angry guy in the shed, no, that one. Now, so Dell and others would not commit to a model, so they in fact unkind to those people who do commit to a model. So that's very clever, actually, because if you don't commit to a model, then you can't be criticised for what model you believe in. So people like Dell will say, well, it's demonstrably a plane, but that's all we know about it. That's pretty lame, actually, because how much time do you need to explore it? If you think it's just a plane, go have a look. What is there? Surely people have been around it, this plane. What evidence is there about where it is? Do you think nobody travels? You think everybody gets stuck in around the west part of Scotland and they don't move anywhere? Or maybe the people in Australia don't travel anywhere? So obviously they do, and because they travel places. One is that's how they know that it's spherical, and two, they have a pretty good idea of the extent of it. Okay, I digress. So, the distance to the Sun. The other one is a Venus transit. So this happens quite infrequently because it takes 243 years between these transits. And they basically come in pairs. So 243 years plus 8 years after that will be the other one. Then 243 years after that, 8 years after that will be the next one, and so on. So you can see that it's a long time in between. So therefore, it's a long time in verifying it. But this has been done over a very long time, so they've had quite a few opportunities to get this right. And again, have got pretty accurate with this. Okay, now we know it's accurate because along comes the next one, which is the modern one, by the way, and just been revised recently, and that is using the mass, time, and of course the path. So we know that it's an elliptical path because, well, you know, like we can follow it. Okay, we can see how it behaves according to stars, because the stars are pretty still, so the sun moves in relation to them, and we can see pretty much that the sun that we're actually taking an elliptical path around the sun, and then using that we're able to use some basic geometry. We're able to use the mass and the time to be able to establish the distance to the sun. Now, establishing the distance to the sun is a pretty useful thing, because then it gives also will be able to give us some pretty accurate information about the size of the sun. Knowing the size of the sun and its composition, which I'll explain later, will then also be able to tell us the mass of the sun. Now, we can then use that also to verify our other means of finding the mass of the sun, which again I will discuss with you. Okay. All right. So this is the modern way now, and it relies basically the modern way on information that we do have, and that they come from Kepler and Newton, and by the way, with adjustments made because of space-time and Einstein. But basically, I'll show you how they actually do this. So there's a little bit of maths in this. Just try and pay attention to it. It's not that difficult, and I'm sure that you'll be able to get it if you just follow it a bit. Okay, so you maybe feel like turning the video off now, but please don't. Watch this. You might actually get something out of it. Okay. All right, so let's have a look at it. First of all, you've seen this top one, quite a lot. So F equals big G M1 M2 over R squared. And we know big G because that's been calculated with experimentation. One of those would be like Cavendish and so on. This is a verified number. It's extremely precise. a very, very precise number, and it's been recalculated and redeveloped and redeveloped, and the number doesn't change insofar as its basic amount is, but in its precision. So in other words, more decimal places, if you like. Okay, so the number, it just gets better and better the more, with the better equipment that we have to be able to do these experiments with, to calculate big G. Okay, and of course this is a very, very important calculation for us, big G, because there's so many things now in satellites, clocks, astronomical clocks, and telescopes and the like, that we actually rely very heavily on the precision of this number, and therefore that's why its pursuit of even more and more precision doesn't stop. Okay. All right. So F is also, so F meaning force, is also equal to mv squared on r. So this is basic circular motion. Okay. So F is mv squared on r, and F is also g m1 m2 on r squared. So it follows, if F is both of those things, then both of those things are equal to each other. So g m1 m2 over r squared is also equal to mv squared on r. That should be pretty close, pretty obvious. Okay, now have a look a bit further down. We've got v equals 2 pi r on the period. Okay, so t is the period. Period meaning that that is the amount of time it takes to do something once. Okay, so the period for the Earth is 24 hours. Okay, it takes 24 hours or close enough for the Earth to go around once. That's the period. Okay, the period for the Sun, for the Earth to go around to orbit the Sun, 365 days or thereabouts, and that's the period. Okay, so 2 pi r, which is the circumference of something, and then divided by the period gives us the velocity. Now, if you replace velocity in the formula, F equals mv squared on r, and also g mm m1 m2 over r squared. If you replace velocity in this one, mv squared on r, okay, then we can then derive this formula. Okay, here where we've got m equals r cubed 4 pi squared on g, and divided by t squared. Now, this is remarkably like Kepler's law. So, and that's not surprising because Kepler's law works. Okay, we have satellites up there. We rely on Kepler's laws, which is r cubed over t squared. So if you take out because mass doesn't matter for a satellite in terms of how far it is and its period, it's irrespective of mass, we can then reduce this to r cubed over t squared, which is Kepler's law and Kepler's Kepler's equation, right? Okay, ratio, that's the word I was looking for. Okay, so how do we know what a satellite is and where to put a satellite? Okay, say for instance a geostationary satellite has to be, it's got to stay in the same place all the time, because you've got your TV satellite dish pointed at it, and it's only give or take, about an inch or so, and if you get it wrong, then you're not going to get a good signal. So you've really got to get this thing pointed correctly. So it's obviously got to stay in this one spot, very, very accurately. People don't go on their roof adjusting their satellite dishes every day. Let me see, I've had mine for at least 10 or 12 years, and I've never once tried to adjust it. The satellite dish guy came along. We had a bit of a yarn for obvious reasons, and he pointed the satellite dish at the right place, and I get perfect television signal because of it, and I've never had to touch it. So that satellite's been up there since I've got into this house, and since I've got this satellite dish. Okay, it's never caused me any issues, and I've never had to readjust it. So the satellite hasn't drifted at all. Okay, I've heard it said that satellites are on balloons. Well, that is just absolute nonsense. That would mean that everybody would be getting up there, adjusting their satellite dish, because the balloon drifts. I mean, what do you think holds the balloon? What do you think keeps it tethered up there? And even if you did have it tethered to a 122,000 feet string, you don't think it would move? Can you seriously be an adult and believe that nonsense? That I would have my dish for 10 to 12 years, never touched it, and it's pointing at some balloon that can wander around anywhere? Come on. Now, let's carry on. Okay, so this is how we've got the distance to the sun. So the sun is not 7 miles. It's not 3,000 miles. It's in fact 1.49 by 10 to the 6 kilometers. Or 1.49 by 10 to the 9, which is a billion, meters. Okay. What's the next thing?